So in the previous class, we discussed different types of controllers. So the controllers are classified based on different categories. So the basic types of controller is proportional controller. In the proportional controller, a controller output will be proportional to error signal. Next, integral controller. In integral controller, the controller output will be integral of error signal. Derivative controller. In the derivative controller, the controller output will be derivative of error signal. In the previous class, we discussed all the types of controllers along with their characteristics. So, the characteristics of the controllers will state that if you use proportional alone, if you use integral controller alone, if you use derivative controller alone, it is not fit for practical system, since there is some limitations what we have seen. In proportional controller, design of proportional gain is somewhat difficult, and in order to maintain one, that is also difficult. Hence, proportional controller alone will not fit for the system. If we take integral controller, in integral controller, the response of the system will be slower because of integral control action. There will be a divided by S term that increases the order and type of the system, because of which the system will tend to become unstable. That is the limitation of integral controller system. Derivative control system. The derivative control system will directly respond to change of error. Because of that, it will take early corrective actions before the output of the system will be true. So, this is one of the limitations of proportional, integral and derivative controller. To overcome this, what they have done is, they have integrated, they have combined proportional and integral controller, proportional and derivative controller, proportional, integral and derivative controller. These are called as composite control modes. So if you take proportional, integral and derivative control alone, those are called as continuous control mode. So PID alone, it is a continuous control mode. Continuous control mode is one which changes the controller output with respect to time. If you take at time interval 0, the output will be different. If you take time interval 10, the output will be different. The output of the system will be continuously varying with respect to time in case of continuous control mode. Also, we discussed discontinuous. In discontinuous mode, it does not vary with respect to time. In discontinuous control mode, there are again two. One is on-off controller and another one is multi-position controller. These two we discussed in the last class. In this class, we will be discussing composite control mode. Composite, the name itself indicates it is a combination. In composite control modes, there are three configurations. One is proportional plus integral type configuration. It is called as PI controller. Then proportional plus derivative controller, it is called as PD controller. Also proportional plus integral plus derivative controller, it is called as PID controller. So these are the classification under composite control modes. It is a combination of one or more continuous control modes. So let us see in detail what are these things. So first I will take up proportional plus integral controller. In the exam, if they ask, explain proportional plus integral controller, then you have to explain this. You should not explain proportional separately and integral controller separately. You have to explain in combination. This thing you have to explain. This is also called as PI type controller, proportional plus integral type controller. The first thing is the definition. The definition of proportional integral controller is a controller in the forward path which changes the controller signal to proportional as well as integral of error signal. So here it is changing proportional plus integral of error signal. So this is controller output. What we have defined is M of t. So if you write proportional control action, it is K, plus integral control action, it is integral of Ki, where Ki is proportionality constant for integral controller. So this is integral of error signal, and this is just K into E of t. Again, we have to convert time domain into frequency domain. For that, we will be using Laplace transformation. If you apply Laplace transformation for this, it will be M of S will be equal to proportional, it is K. E of t becomes E of S. I will take E of S as a common here, plus in integral control action, if you apply Laplace transformation for integration, you will get divided by S. And this will be, in detail, we will be studying in module 2. It is Ki by S into E of S. So E of S is the error signal in frequency domain. E of t is error signal in time domain. So when you take the ratio M of S divided by E of S, so this is nothing but it is a transfer function or a mathematical model for proportional plus integral controller. It will be K plus Ki by S. So this is transfer function for proportional plus integral controller or PI controller. This is the equation. Again, in this equation you have two terms. One is K. K is constant of proportionality for proportional control action, and K suffix I, that is K varies. Again, the system tends to become unstable. If Ki varies, again the system tends to become unstable. So we need to ensure the proper values of K and Ki in the designing of PI controller. Let us see the block diagram of proportional plus integral controller. So this is R of S. R of S is the reference input signal, then a controller. Here the controller means it is having two types. One is proportional as well as integral control. So proportional control, I will be calling it as K, and then integral controller, I will be calling it as Ki by S. These are the two blocks which represents the transfer function for proportional as well as integral control action. And this is summing point. That means the signals are being integrated. After that, you have a manipulated signal M of S, then followed by a process or plant. Generally, in the previous sessions, what we have considered is we have considered second order system for the analysis, because it is very important to know the behavior of second order system, which will work exactly as a practical system. So that's why omega n square divided by S into S plus 2 zeta omega n. Second order system has taken into considerations. This is plant and this is controller. So here controller means proportional plus integral. So I will write PI. Then output, controlled output signal, then again a feedback which measures the output. So here we have considered unity feedback system. So this is a block diagram of PI controller. While writing block diagram, you have to ensure that proportional as well as integral block diagram will be parallel to each other. So that is one of the important thing, because here there is a sign plus. Proportional plus integral control action will play majorly on steady state response. Whenever if you consider the steady state response, proportional plus integral controller will be dominating, because initially there is a S square plus 2 zeta omega n plus omega n square. That is a characteristic equation for PI controller. When we add an integral controller, there will be a S term which is induced. So this S term is causing increase of frequency domain, which is flexible for steady state response. In other words, what we can say is proportional plus integral controller will be good for steady state response. But because of change in order and type of the system, that is S term will be increasing, because of which the transient response of the system will be affected, because of damping will be affected, the amplitude of vibrations will be varied. Because of this, we won't get stable output in case of PI controller. That is a limitation of this. So let us see the characteristic graph of PI controller. Characteristic graph is plotted, controller output, I will just write C of t versus time. When I take proportional, it is proportional. This is a proportionality graph or proportional controller graph. When I take integral controller graph, there will be some amount of amplitude at the initial, and due to the phase lag, the response will be like this. This is a response for PI controller. As you know, initially at time 0 the input is more, or the amplitude of the signal is more, and then it is increasing linearly. This variation is because of integral control action, and initially it will be behaving like proportional control action, later integral part will be added. The characteristic of integral part is slow response of the system. So after some value the characteristics will be slow. So that is undesired in case of a practical system. So in order to avoid this, what we will do is we will integrate proportional integral with proportional derivative controller, that will be exactly PID controller. So let us list what are the characteristics of proportional integral control action. As I already said, because of increase in S, the order of the system increases. That is the first characteristic, the order of the system increases. Because of this, even the type of the system also increases. Let us see in detail what is the order and type of the system in module 3, response analysis. Again, in proportional control action, designing of gain, and that gain will be equal to 1 is very difficult. As constant of proportional for integral controller. So there are two gains in the system, because of which what happens, the system tries to become unstable. Also, before that, in integral control action, the Ki, the suffix Ki is not perfect. The value of Ki will be changing periodically, and that will lead to slow response of the system. Compared to proportional gain, we have to take care of integral gain. So design of integral gain should be proper, otherwise it leads to instability of the system. That is another important thing. And overall, what is the advantage of PI controller rather P controller? The answer is the steady state response. Here it improves steady state response as you change the value of frequencies, even the transient response is also getting affected. That is important thing. Here it improves steady state response but affects transient part. Affecting the transient response of the system is one of the limitation in case of PI controller. So the only advantage what I can quote is the steady state response. Let us see how the steady state response will be. So if you take a second order system, this is a response of second order system. So second order system will be corresponding to underdamped vibration. Here there is a continuous oscillations with respect to mean position. This is undesired in any practical system. If you have vibration, the system must be rejected. Finally, the system fails. The frequency at which the oscillations occurs, we need to encounter it. Also, the amplitude of vibration. So, in integral response, what it will do is, it will maintain amplitude of the response to certain value, and for that amplitude, the system goes on vibrating in each cycles. At each cycles, the amplitude will be constant. That means it is not varying with respect to time. If you measure the amplitude at time 0, the amplitude, say for example x at time 0, the same amplitude will be there at every cycles. If you measure nth cycle of the time, the amplitude is always x. That's why it is called as steady state response. So this is a characteristic of underdamped vibration. So this vibration is undesirable in all the times. I want the more amplitude at first in order to start the system, because in starting of the system I need to overcome the more force in order to overcome the inertia. So because of which I need more force initially. After that I don't want any forces. That means initially I want the response to be high, and after that the response to be stable and should be decayed. So this is the practical response of the system. This steady state response alone is undesirable in nature. Let us take the transient response of the system. The same steady state response is being changed with the help of suitable damping. If we apply damping for the system, initially the vibrations will be high, then after that low, then finally the amplitude will be decays. So if you take the amplitudes graph, the amplitude will be decreasing exponentially. The corresponding term will be used for logarithmic decrement of the amplitude. So initially I want higher amplitude to overcome the inertia force of the vehicle, then after that the response should be slow and amplitude should be decays. This is the graph for stable system. And here if you measure amplitude at each cycles, the amplitudes are different. Initially the amplitude at time 0 is x1, the amplitude at time t1 will be x2. That means in each cases amplitude varying. Initially it is having higher amplitude, and final cycle the amplitude will be almost 0. This is the amplitude variation with respect to time in each cycle. Since time is varying in each cycle, this response is called as transient response. Since the increase of value of S, if you change the value of damping, if you replace S is equal to j omega, omega is the value which will increase the value of damping. If you change the value of frequency, then what happens? The damping will also changes, but the amplitude will be constant. Initially the graph will be like this in PI controller. If you change the value of omega, it will be higher amplitude. Again the vibrations will be continued through a constant mode. That is one of the limitation of PI controller. Let us take second type of controller, that is proportional plus derivative controller. That is nothing but PD controller. The name itself indicates derivative controller. The same analogy. Here M of t is the controller output. Here controller output is proportional to derivative of error signal. Proportional means k into E of t. Derivative is nothing but, I will take a constant of proportionality for derivative constant, that is k suffix d, into derivative, that is d by dt of E of t. If I apply Laplace transformation for that, since there is a derivative term, the s will get multiplied and it will be s into k suffix d. The manipulated signal of the derivative controller will be k plus s into k suffix d. The definition of derivative controller is a controller in the forward path which changes the controller output proportional as well as derivative of error signal. That is the definition. Again the same thing, the manipulated output will be K plus S into KD into E of S, error signal in frequency domain mode. And finally the transfer function for derivative controller will be K plus S into KD. The same block diagram, only the change is instead of Ki by S, it will be K suffix D into S. This is a block diagram for PD type controller, proportional plus derivative controller. Again, the characteristic plot of proportional plus derivative controller will be like this only. Only the change is after the time intervals, the amplitude of the vibrations will be changing for the corresponding frequencies. And the characteristics of the system is different here in case. Already you know the derivative controller will be responding to change in error. Since we have combined derivative controller with a proportional control action, already there is an output. For that output, the next cycle will be, the output will be modified or amplified. Or the proportional derivative controller is, I am maintaining 80 km per hour proportionally. Suddenly if any dog or anything comes nearby my vehicle, then I have to apply brake suddenly. That control action is, I need to reduce the speed immediately for the proportional output. That is the one of the example for PD controller. PD controller will be working like that. Already there is a controlled output. That means you are maintaining 80 km per hour. For that you have to respond. If any obstruction is there, then you will be reducing your vehicle speed suddenly. If there is no obstruction, again you will be increasing the speed of the vehicle. PD controller is, already there is output. For that you will be or you will be maintaining or you will be increasing the output. So that is the one of the characteristics of PD controller. Here the main characteristics of PD controller is the amplitude of the vibration will be going decrease because of S term in the denominator. There is a S term in the denominator. That S term will be reducing amplitude of vibration. That amplitude of vibration is reduced because of damping. So the first property is it exhibits damping. The second one is, once if the system is having some amount of damping, means you can change the frequency. So omega n you can alter, you can keep the same, you can change anything. So you have a provision to alter omega n. That is circular frequency of the system. Then the type and order of the system remains constant. Again, you will be knowing what is the order of the system and type of the system for various response inputs. So that will be dealt in module 3 in detail. Then when you have transient response of the system, here there is no deviation for the amplitude. So the overshoot of the system, that is called as peak overshoot of the system, will be reduced. Also, due to damping, there is no non-linearities occurs. That means sudden rise of output or sudden decrease in output, that will be not there. And here rise time and settling time will also be less. That is one of the characteristics of PD controller. And PD controller will improve transient response without affecting steady state response. So these are the important characteristics of PD controller. So number one, it exhibits suitable damping because of value of S. Then You can change the frequency, you can alter the frequency, and you can maintain the same frequency. There is a provision to alter the frequency. Then order and the type of the system will be remains constant. Even you can keep frequency is also same in all the cycles. Then peak overshoot will be always be less. The output will not get deviated because of some environmental changes or distortions. Then it is having a less settling and rise time. Always rise time and settling time is very important in case of any design in control system. Rise time, some cases if the output is suddenly fluctuates, if you are going 80 km per hour, if you give a small amount of increase in acceleration, if it goes to 200 km per hour, then accidents, everything will happen because of uncontrolled system. That we need to reduce here. That is very important thing. Because of transient behavior of the system, that will be reduced. Then it improves transient response. Transient response is improved because of damping only. Here transient response is the amplitude of each cycles will be varying because of damping. So since it is having improvement in transient response system, this will be added later to the system. Then it will not affect steady state response. That is one of the important thing and important characteristics of the system. Initially I want higher amplitude. This higher amplitude you have to obtain only in steady state system. Because of that depends upon your dynamics of the system. Spring mass system, if you solve the equation of spring mass system, the final differential equation will be stating what is the response of the system, that is steady state response of the system. Then after that, if you increase, if you add force, if you add any damping, if you add any dynamic behavior, if you convert any dynamics, that means adding force, excitation, electrical, etc., that will be doing transient system part. That means in differential equation, if RHS is equal to 0, then there is no transient part. If RHS is not equal to 0, then there is a transient part. In any differential equations, there are two parts. If you solve, y is equal to complementary function plus particular integral. The complementary function will tells about steady state part and particular integral tells about transient state part. So in the differential equation, these two are very important in case of any practical system. And these things you will be solving in detail in module 2. Don't worry about that. Just you remember steady state and transient state response. Steady state corresponds to complementary function. Transient state is corresponding to particular integral. Again, the limitation. Here, sir, can I vary the steady state response? No, we cannot vary this. But we can keep steady state response as a constant. But where to get this steady state response? Again, we need PI controller. So, you have seen PI controller, you have seen PD controller, you know what is the characteristics of PI controller. It improves transient state response. PD controller, it improves steady state response. But in practical system, I want both steady as well as transient state response to be improved. Again, take an example of manual speed control system. 80 km per hour is the reference input. Sometimes I want to maintain 80 km per hour. Sometimes I will be going at 60 km per hour. Sometimes I will be going 100 km per hour. I need to have a provision to increase or decrease or to maintain the speed. So whenever we want this provision, the controller should be like that. Our brain is a God-gifted controller. It will control everything. No problem in that. But whereas a physical system, we need to design that type of controller. It should have the capability of maintaining the output, maintaining the increased output, maintaining the decreased output. For that, we need to design a controllers like this. PI controller will be decreasing. PD controller will be increasing. So what I have to suggest? What I have to want? I need practically PI will not used, PD will not be used. Practically only controller exists is PID controller. Proportional plus integral plus derivative controller. That is a practical controller will be used in every systems. Because of advantages of PI controller and advantages of PD controller, both are mixed and PID controller were developed. PI controller will improve steady state response, PD controller will improve transient state response, PID controller will improve overall response of the systems, and that is a flexible in case of a practical control systems. Let us take the next type of controller, proportional plus integral plus derivative controller. So, this is also called as PID controller. The definition for PID controller is a controller in the forward path which changes the controller output to proportional, integral as well as derivative of error signal. Let us write that. So, controller output is m of t will be proportional plus integral plus derivative of error signal. The proportional controller is k into e of t. Integral controller will be integral of k suffix I into e of d. Derivative controller is d by dt of k suffix d into e of t. So, these are the individual controller gains. K is constant of proportionality for proportional control action, Ki is constant of proportionality for integral control action, Kd is constant of proportionality for derivative control action. Again, we need to convert the t domain into s domain, time domain into frequency domain. So, what I will do is basically I will apply Laplace transformation. So, if I apply Laplace transformation, m of t becomes m of s, k of e becomes k, plus k into e of s, I will take e of s common for all the terms. Whenever there is an integration, you will get divided by s. Whenever there is a derivative, you will get multiplied by s. So, this is the gain for PID controller into e of s. Again, mathematical model for this is output will be m of s, input will be e of s, this will be equal to k plus ki by s plus s into kd. So, this is a transfer function or mathematical model for PID controller. Again, the same thing I will be writing in terms of block diagram. This is a controller or error detector, reference input signal R of s. Here there are three terms. One is proportional, that is nothing but k. You can make k is equal to 1, that is also possible. Then integral ki by s, then derivative s into kd, and all these blocks are parallel to each other since there is a plus sign in between. And this is passed to a summing junction. The plant is always a second order system. It will be omega n square divided by s into s plus 2 zeta omega n. And C of t is, C of s is controlled output signal, and this is a feedback signal which measures the output. So, this cumulatively, it is a PID controller, and this is plant. The plant can be first order system or second order system. The practical system is always second order system, that's why we will consider second order system for analysis. This is a characteristic graph for PID controller. This is proportional, this is PI or PD, the same thing, and this is a PID controller. You will get a parabolic graph for PID controller because of S. And the main characteristic of PID controller, it will improve the overall response of the system. Since there is a PI controller. PI controller will improve steady state response and PD controller improves transient state response. The combination of PI and PD controller will improve the overall response of the system. Let us take an example of PID controller. Initially, I want some amplitude, I want some increased force to overcome the inertia. Because in the static load conditions, moving the vehicle is different. When dynamic load conditions, moving the vehicle is different. So, when vehicle is at off position, pushing the vehicle or pulling the vehicle is very difficult because of more number of parts that will have more inertia. We need to overcome the inertia force initially. That's why the graph will be high. The amplitude of vibrations will be high at initially, and this amplitude is because of steady state response or complementary function in differential equation. After that, we need to reduce the amplitude. How to reduce the amplitude? By exhibiting suitable damping. After that, it will be having some amount of damping. Finally, it will be decayed. And this has to taken place within a short span of time, say for example within 3 to 5 milliseconds. That is the accuracy in electronic system. After that, it should exhibit a straight characteristic or linear characteristic or direct current characteristics. This is very essential in case of practical system. So this can be achieved in PID controller. Initially, PI controller will be taken care of amplitude of vibration. After that, PD controller will exhibit suitable damping and reduce the vibration, and finally reduce to zero, and finally we will get a stable output. This stable output is nothing but a manipulated signal. And finally, this can be expressed in terms of time domain specifications and frequency domain specifications. So whenever they ask a characteristic, write the characteristic graph and explain this, and you can combine the advantages and limitations of PI and PD controller. So advantages of limitations of PI controller, limitations of PD controller is advantages of PID controller. The only limitation of PID controller is cost and number of components. PI controller will have some network, PD controller will have some network. Those network cost is more because of number of elements. And essential in all the control systems, we will be using PID controller. So this is about control action and controllers. In control action and controllers, we discussed proportional controller, integral controller, derivative controller, proportional plus integral controller, proportional plus derivative controller, proportional plus integral plus derivative controller. So anything can be asked in the exam. If they ask, you have to write the definition, then followed by a block diagram, then a transfer function or a mathematical model, then a characteristic and graph. So these things you have to write compulsorily. This will be asked for 7 marks. First you understand the question and then write. And while correlating PI and PD controller, there will be a difficult. So just you remember PI and PD controller correctly. PD controller will be improving transient state response. PI controller will be improving steady state response. By remembering the graph of transient and steady state response, you can write the explanation for PI and PD controller. So this is about module 1. In the module 1, we started with introduction to control system, the definition of control system, the classification of control system, open loop and closed loop system, examples for open loop control system, advantages and disadvantages for open loop control system, classification of closed loop system, that is regulatory control system, follow-up system and servo mechanism, and advantages of closed loop control system, also the examples of closed loop control system like manual speed control, temperature control system, missile launching system, and ship stabilization system. After that, advantages, limitations of closed loop control system along with comparison of open loop and closed loop control system. Then the requirements of a control system, ideal requirements of the control system. Then after that, we started with control action and controllers. In control action and controllers, the definition of control action, the definition of controllers, and the types of controllers, PID, PI, PD, and PID. So this is about the module 1. Thank you.